it's been pretty amazing to be kind of at the forefront, at the cutting edge, to see all the luminaries in the field, and you find out that these big names are just people with a lot of common interests that overlap with yours, and who will only be too happy to talk with you about them.
Hello, everyone. Thank you for coming to my talk today. This is my third time talking at CppCon, and today we're going to be talking about weight-free algorithms, right? So topics in concurrency and concurrent programming. My name is Daniel. I'm a teacher at CMU. I teach algorithms classes to undergrads. I don't usually teach concurrent algorithms to undergrads. I teach them, more boring non-concurrent algorithms, and I do concurrency in my spare time for fun. But today we're going to be talking about concurrent algorithms. So very excited to be here. My third time here at CppCon, although it's my first time in the big room. So that means someone thought my talk might actually be good. So I'm going to have to try and live up to that expectation. So what are we going to cover today? Just a quick overview. So we'll start by just reviewing the basics, the main ideas of concurrency very briefly, and lock-free programming. And then we'll sort of review, what I say is the bread and butter of lock-free design patterns, right? You may have seen a talk or two on lock-free programming. There's usually, a dozen of them at every CppCon every year. It's a very big topic. So we'll review what I think are the bread and butter really of the design patterns there. And then we will motivate and define weight-free algorithms. Okay, so we'll try and understand what that means, what are the implications, how are we improving on so-called lock-free algorithms, and then we'll go through an example. Pretty much the whole talk will be driven by this one example of a weight-free algorithm and the thought process and design ideas that go into making that work. And we'll do a tiny bit of benchmarking. Not very much, but a little bit. So just some assumed background knowledge, since this is a talk about concurrency and weight-free algorithms. There is some assumptions built in that you have at least the sort of fundamentals down. You've heard of std-atomic, I hope. You know roughly what std-atomic does. You don't need to know about memory models for this talk. So if you don't know about memory orderings and the memory model, that's okay. We won't get into that in this talk. There are plenty of really good talks by people much smarter than me who understand that stuff much better than me about memory orderings and that sort of thing. So we won't go into that stuff today. It's sort of orthogonal to what we're talking about. But you should know what std-atomic does. And hopefully you have seen a little bit of lock-free programming before. You don't have to be an expert, but hopefully you've been to one of the many excellent talks on lock-free programming, or you've done a little bit of it yourself. Okay, so let's dive into it. So our motivating problem today is sometimes referred to as a sticky counter data structure. It's a bit of an obscure name used in some fields. It's not a widely used name. If you Google it, you probably won't find weight-free algorithms. You will probably find information about cleaning your kitchen. Okay, so this is not quite a well-used term, but it's used by a few people. And the idea is we want to implement a counter, an atomic counter that you can increment and decrement, but it gets stuck at 0, hence the name. And so the operations we want to support are increment the counter if it isn't 0. If it's 0, don't increment the counter and tell me. I couldn't do it because it was 0. I'm stuck. And decrement the counter, right? So that just decrements the counter. And if it equals 0 now, tell me you're the one who stuck the counter at 0, right? You're the one who got it stuck. Now no one else can increment it. Good job. Okay, and as a precondition, the counter can't already be 0 if you're decrementing. We don't want negatives, don't go lower than 0. And of course, a read operation. We want to be able to read the current value of the counter. Now, you might think, okay, is this a contrived example? I claim that, okay, this definitely, hopefully isn't a contrived example. In fact, if your standard library supports C++11, probably does by now, I claim that your standard library has this in it somewhere. Maybe not with this exact API, but your standard library has to have this. Any standard library nerds who want to guess like where this is in the standard library? It's a bit obscure, but yeah, any ideas? Yeah, in shared pointers, more specifically actually. Who can give me an even more specific answer? Yeah. Weak pointer, yes. You need this for weak pointer lock specifically, right? So if you have a reference counted shared pointer, you have some reference counted object, and you have a weak pointer pointing to that object. The weak pointer doesn't own a reference count. It just says, I'm going to point to that guy, and if you want to read the value, you're going to have to, upgrade yourself into a shared pointer. That's the lock method. And doing so needs to increment the reference count. But if it's 0, you don't want to increment the reference count. The object is long gone. You want to just instead return a null pointer or throw an exception, because that object has been long deleted. So this is not contrived. This is something your standard library has in it already. And it's also very useful for other concurrent algorithm problems. It's very useful for atomic memory management and data structures. In particular, if you saw my CppCon talk last year, where I showed you how to implement an atomic shared pointer using SMR techniques, we used this exact API. We needed this operation. Okay, so it's very useful for reference counting and memory management and that sort of thing. Okay, and that's the kind of stuff I'm interested in, so that's why it shows up as our example. Okay, so this is the problem that we want to solve. How are we going to do it? So very quick, starting point. Okay, well, you ask someone to write the code for this. Here it is, right? They write the code. Looks correct to me. I mean, it works, right? If the counter is not 0, we'll increment it. Otherwise, we don't. How hard is that? Well, this code is correct, but it's perhaps missing some crucial property that we want, because this is a talk about concurrency. What are we missing here? We're missing maybe one little property we really want. Yeah, is it thread safe? Is it atomic? No, this is not a thread safe implementation. It's not an atomic implementation. The issue, of course, that happens is, okay, we have a thread. Here's thread 1. He starts running. If count is greater than 0, true, okay. And now this thread goes to sleep. Operating system decides that you've had too much time. I'm going to let someone else use this CPU. Okay, so now thread 2 comes in and says, I'd like to decrement the counter, please. Thread 1 wakes up from its nap. It's in the yes branch. It says, I'm going to increment the counter. But it was 0. That decrement said I set the counter to 0. So no one's allowed to come and increment the counter anymore. So clearly we are missing some thread safety here, okay? So how do we take something that isn't thread safe and make it thread safe? Well, we can start with the fundamentals, right? The place that we all learn first, which is we can throw in some locks. And we can put in a mutex and take a lock guard around those operations. And so now, if multiple threads want to call these operations, this will be safe, okay? No more interleaving of those operations. So this is, once again, this is a correct implementation. In fact, it's even better. This is a correct thread-safe implementation. But it's not my favorite implementation. What can go wrong? Maybe not so much wrong, but undesirable. Thread 1 comes in, takes the lock, starts the operation, goes out for lunch, right? Gets descheduled, goes on its lunch break, takes the lock with it, right? Takes the lock and leaves. Now thread 2 comes along, I'd like to decrement, please. Lock says, no, not yet. You've got to wait for that other guy. He's got the lock, okay? But maybe he's gone out, the thread has gone out for lunch with the lock. He's going to be back in a while. So, we just wait a bit. And, okay, eventually thread 1 comes back and finishes its operation, and thread 2 can proceed safely. Everything that happened is correct here, but the issue is thread 2 was very unhappy with its performance. Thread 2 says, well, I'd like to do some work. No one else is doing anything. Why can't I do some work? I would like to, operate on this data structure, but I have to wait for the guy who took the lock to lunch. Nothing's happening, right? So our algorithm is making no progress. It's just sitting there waiting. So, to summarize, right, locks, the first thing we learn with concurrency, they're very effective at solving most problems in concurrency because they do so by eliminating concurrency. They simply don't allow any concurrency to happen at all. So this means often, but not always, of course, important disclaimer, locks are very useful and can be good performance if used in the correct circumstances, but often locks have, bad performance implications, okay? Especially if not used extremely carefully and benchmarked very carefully. But of course, necessary disclaimer, always measure performance, never guess. Okay, so we shouldn't just guess that the lock is worse. We can hypothesize, but we should benchmark. Okay, so never guess about performance. That's the title here. The rest of this talk, how to guess about performance. But then we'll benchmark, okay? Don't guess about performance means don't guess and then ship it. You can hypothesize, then test your hypothesis with some benchmarks. So it's good to hypothesize about performance with some kind of theoretical analysis, but don't just guess and ship it, okay? So what do we need? We need some vocabulary to talk about, good versus less good concurrent algorithms, right? You've probably heard, the term lock-free. I mean, you've definitely heard it. It's in the title, I told you, but you've probably heard about lock-free, and if you aren't an expert in the subject, you may think, well, lock-free means no locks, obviously, duh, like what else could it mean, right? So lock-free just means no locks, right? I should Control F, mutex, 0 matches, my code is lock-free, right? No, that unfortunately, and you can blame whoever came up with the term lock-free, it's a slightly misleading phrase. Lock-free doesn't just mean don't use locks. It's a little bit more subtle than that. Now, 90% of the time, that is actually accurate, right? Like they do coincide 90% of the time, but it's not always the case. There is such a thing as lock-free locks. It's very mind-bending, but it exists. You could also write algorithms that are not lock-free without putting in a mutex. I mean, you can spin on a variable in a loop. Like that's also just going to block as well. So we need some vocabulary to talk about these things more formally, and we're going to see the real definition of lock-free as well. So we phrase, the performance guarantees, the progress guarantees of a concurrent algorithm in terms of these things, progress guarantees, and we have a few of them. Okay, it's a way to theoretically categorize our algorithms. The first I'll call blocking. I like blocking rather than locking because it doesn't imply, this is less misleading. You don't think mutex when you hear block rather than lock. Locking means no guarantee, no progress, right? Our thread before, thread 2, came in, wanted the mutex, but someone else had it. Unfortunately, the guy that had the mutex wasn't doing anything. He was out for lunch. No progress was being made. Okay, so that's like the worst thing you can have, right, is just blocking. No progress whatsoever. The first thing we can define that gives us anything is what is called obstruction freedom. Okay, and obstruction freedom intuitively means you get progress in isolation. So if you just have a single thread executing in isolation by itself, like it will complete in a bounded number of steps. This essentially means you don't get deadlock, right? So if you're the only one, around, right, something happens, right? You can't deadlock where, two people are they're both there trying to do things, but they're both just blocking each other doing nothing, right? So one guy by itself should do something, okay? The next best thing, okay, this is the actual true legal definition of lock-free. So lock-free intuitively means at least one thread makes progress. So at any given time, if there are a bunch of threads, who want to make progress, they want to complete their operation, then at least one of them makes progress for some definition of progress, right? You get closer to finishing your operation. And this is nice because this gives you guaranteed system-wide throughput. It means that some operations are completing, right? Stuff is always happening, progress is being made. The downside is that it doesn't tell you anything about any particular operation. It's perfectly legal in a lock-free setting for there to be one operation, right, one thread, who's making no progress. He's stuck. As long as other threads are continuously making progress, that's legal. So you know that there is progress being made, operations are succeeding, but individual operations could starve. They could get no progress. at the expense of the operations that are making progress. Okay? So now you may guess, okay, what comes next then? At least one thread makes progress. How could we make that better? Well, maybe all threads make progress. And that is the definition of a wait-free algorithm. So at any given time, regardless of other competing concurrent operations that are there trying to mess with us, all the threads are making progress. Okay? Every operation is going to complete in a bounded number of steps. You're never going to get stuck looping forever, trying something that's not working. Okay? So this gives you like a guaranteed bound on the completion time for every operation, right? This is, in a theoretical sense, basically a guaranteed worst case latency. You know, in practice, it's not necessarily a worst case latency because you could get descheduled. You don't know how long it's going to take to get rescheduled, but it's essentially guaranteed theoretical latency in terms of how many operations it takes. Okay? As opposed to lock-free, where you know some operations are going to be completing, but this one operation might be stuck, theoretically forever. In practice, probably not forever, because your operating system schedule is not that mean. But in theory, we can't put a guarantee on it. We can't put a bound on it without talking about fair schedulers, which we're not going to. So that's our vocabulary. Those are our formal definitions for talking about lock-free and wait-free algorithms, and those that aren't. We rarely talk about obstruction-free. I mean, it's there, it's useful, but we don't talk about it too often. People typically try to aim for the bottom two. Lock-free is like, good, right? Like you've seen handfuls of talks every year at CppCon about lock-free something. I'm sure if you look at the schedule this year and Control-F lock-free, it's going to be there a bunch of times, right? Lock-free is like the popular good thing to aim for. But if we're lucky, maybe we can do better. We often can't. Like wait-free is not always achievable. It's the gold standard. It's very difficult to design and implement a wait-free algorithm. We're going to do one of them today, but a lot of problems this is extremely difficult or maybe impossible. So let's go back to our motivating example, our sticky counter, and let's think about how we can go from, so far we only had like the lock algorithm, the blocking algorithm. So far we didn't have anything, right? So we want to somehow do better than that. So if I have my counter here, the first thing we're going to do is take that counter from just being an int and stick it in an atomic, right? We need atomics. If we're going to do lock-free programming, you need atomics, okay? So first step, stick it in an atomic. That's not the only step, though. You don't just stick it in an atomic and now write exactly the previous code. That doesn't work. You still need to make use of the atomic operations made available to us. So, if you've seen any lock-free programming before, hopefully you have, to implement what we want, our goal is increment the counter if it's not 0. So in other words, we want to change the value of that counter if it is what we want it to be. There's an operation for that. This is the bread and butter operation for this kind of operation. This is compare exchange, right? Compare the value to what I think it is, and if I'm right, set it to what I want it to be. And so your increment, if not 0, can be implemented using the compare exchange. And in particular, a compare exchange loop, right? We have to loop because we read the current counter, and if it's bigger than 0, it's legal for us to try and increment it. We compare exchange, and we say compare exchange current plus 1, which means I think the value is currently current. That was confusing. I didn't think of that. Currently current. It equals that. If I'm correct, please set it to current plus 1. If I am incorrect, if the value doesn't equal current, then load the new value into current. So this actually side effects. It will load the value that it actually contains. And then you try again, right? This is why you loop. This is why you'll very often see in lock-free programming and lock-free algorithms, you'll see these weird empty loops. And people who don't know the exact semantics of compare exchange always think this is a bug. They're like, you forgot your loop body. No, that's because compare exchange, when it fails, it loads, right? In other words, compare exchange is an atomic version of this pseudocode, right? If the current value is what I think it is, then set the current value to what I want it to be and return true. You've succeeded. Otherwise, load in the current value. Like, tell me why I was wrong. No, the value is actually this. And then return false. All right, so this is really this bread and butter idea of a compare-exchange loop, where you keep trying to do the update you want, and if you fail, you just try again. Okay? And our decrement operation, well, we could also do that with a compare-exchange loop, right? We could do almost the same code, but like current -1. But actually, we can do it a little bit faster because we can use this idea called fetch and subtract, which is an atomic way of saying subtract 1 from this number and then tell me what it was. We can do this because this isn't a decrement if some condition holds. Like, we don't need compare exchange here because decrement is just decrement. It's not decrement if some condition holds, okay? So it's okay to do this. And another thing that will often confuse people, fetch and sub, it returns the old value, not the new value. So to check, hey, did I just set the counter to 0? It's if fetch sub 1 equals 1, not if fetch sub 1 equals 0. It returns the old value. So if it was 1, and I subtracted 1, it is now 0, right? I mean, it's in the name. It's fetch, then sub. You get the value, then you subtract. It's in that order, right? And then our read operation, okay, we counter.load, okay? Nothing too special there. So that is our lock-free solution to the atomic sticky counter. And let's again hone in on really what was the bread and butter there? What was the key thing that shows up in 99% of lock-free algorithms? It's the compare-exchange loop or the CAS loop. Theoreticians, people who do concurrency theory, call compare-exchange compare and swap. So they often call it CAS for short instead of compare-exchange. So I'll often say CAS loop. Think of that interchangeably with compare-exchange. The bread and butter technique, right? We read the current state of the data structure. We figure out the new state that we want it to be. We then commit that change only if no one else has changed it. If the old state is still what we think it is, then we commit our new state. But if someone else changed it, they got in first, well, then we just try again, right? We get the new state. We again figure out what we want the state to be and try to commit it with a compare exchange. That is the bread and butter of lock-free design, right? 99% of lock-free algorithms will have a CAS loop or several. So theoretically, what kind of progress guarantee is this? Well, it's lock-free because you might say an operation is never guaranteed to succeed. I could get clobbered forever, right? But here's the trick. If my operation fails, if it gets clobbered, that can only happen because someone else's operation succeeded. So I can only fail to make progress because someone else made progress. I can't fail to make progress because someone took the lock and went out for lunch, right? I can't fail because of nothing. I fail because of something. Someone else did something and made progress. So algorithms like this are usually lock-free, okay? But it is not wait-free. Because even though operations are succeeding, like at any sort of moment in time, if there are a bunch of threads trying to do compare exchange, one of them succeeds. They shouldn't all fail, okay? In theory, at least. We're ignoring compare exchange weak here. In theory, we're assuming the compare exchange succeeds for someone, okay? Someone gets in first. Someone gets in first. The expected value truly is what they thought it was, and their CAS succeeds. So someone is always making progress, but other threads could be stuck forever. Maybe one thread is really lucky and it wins every time, and every other thread loses every single time. If that's the case, those threads are never guaranteed to succeed. They could take an arbitrarily long time, okay? And that's not good for wait freedom. That's not wait free, okay? So this is our tool for lock-free design. What do we do if we want wait-free? So a wait-free algorithm, well, it shouldn't do that. It shouldn't contain an unbounded CAS loop. That does not mean that you can't use compare exchange. in a weight-free algorithm. No, it's still an amazingly powerful primitive. It's still a tool you probably need to use. You just can't use it in an unbounded loop. You can still use it a bounded number of times, okay? As long as you can put a limit and say, I know that I'm not going to do more than a certain number of these, that's okay. You just can't have a potentially unbounded number of these things. So we're going to need to make sure we make use of key primitives here are our favorite tool in our toolkit, the atomic read, modify, write operations. And in fact, you've already seen like 2 of the 3 of these in the previous slides. Compare exchange is our sort of bread and butter one. It atomically replaces the value, if it is what I think it is, with the value I want it to be. With the small subtlety, we have the weak and strong versions of compare exchange. Weak version is allowed to sometimes fail spuriously. It is allowed to say, you failed even though the value was what you thought it was. This just allows compare exchange to be implemented slightly more efficiently on different computer architectures, okay? Doesn't make a difference on x86 as far as I know, but it may matter on other architectures like ARM. So that is our main atomic read, modify, write operation, but we have a few others that are very useful. You saw the fetch sub operation a few slides ago. We also have the corresponding fetch add. Okay, it atomically adds a given value to the atomic variable and returns the original value. And our third one that will come in handy is an atomic exchange. This is basically store, right? Just like atomic store, but you get to find out what you replaced. You find out what value used to be there, right? Unlike a store, which just stores and who knows what was there. So the key theme here, right, with the atomic read, modify, write operations is we know what used to be there. Like we are changing the value, but we always find out what used to be there. If we do a fetch add, we know what the old number was. If we do an exchange, we know what we clobbered. If we do a compare exchange, we know what the value used to be because we had to do the compare exchange. So we always know what we did to the data structure, right? This is very important. That's why it's a read, modify, write operation. We read the value, we know what it is, we modify it, and then we write, all atomically. So these are the key tools in our toolbox that we're going to need for lock-free and wait-free algorithms. So we're going to have to get rid of our unbounded CAS loops and somehow use these to get our algorithms to work in a bounded number of steps. So that's our toolbox. What are we going to do? So again, bread and butter was the CAS loop. The problem was threads clobber each other, right? Threads come in and say, oh, you're trying to change the data structure? No, I want to change the data structure. I go first, and if I win, I wasted your time, right? Like you just wasted time trying to do the operation, you fail, and you have to try again. Okay, so the threads are really competing against each other and they're hurting each other. Okay, one thread's success is another thread's failure. So if we want wait freedom, we don't want threads to be blocking each other and competing each other. So the big idea, right, the key idea here is instead of being like competitive with each other, operations, threads should try to be collaborative instead. You see another operation in progress. Instead of saying, screw you, shove them out of the way, do my operation, you try to help them. You try to help them with their operation and then do your operation so that they're not getting blocked by you. Everyone gets a chance to do their operation. And so the bread and butter of wait-free design, which I would say is the analogy to the CAS loop, it's the ubiquitous tool for wait-free design, for non-trivial wait-free algorithms, is called helping. Right? So helping means that if an operation finds the data structure in a state where it knows another operation is halfway through doing something, instead of clobbering them and undoing their progress, it helps them. It helps them make progress on their operation and then tries to do its own operation as well. Okay? So the threads are now being collaborative, friendly, rather than competitive and hurting each other. Okay? Now, disclaimer, this is not easy, right? Like it's easier said than done. It's not like you can just go and take any CAS loop and convert it into a helping scheme. This is very difficult to pull off most of the time. right? This does mean that you need a way for operations to like detect that another operation is doing something. In a CAS loop, you don't have that. Like if another thread has read the value and has made their update and is now trying to commit it, another thread has no way to detect that. Like it can't not clobber you. It just doesn't know. It doesn't know any better. So this means, we need to design our algorithms in a way where threads can detect the presence of competing operations to help each other. And that usually requires a very big redesign of your algorithm. It's not like you can take your lock-free algorithm and just change a few lines and it's wait-free. No, this usually requires a whole new idea. But that's what we want to achieve, right? We need to figure out a way for threads to be collaborative, for our operations to help each other instead of waiting, which would be blocking, or competing against them. Okay? So now let's see, how can we apply this to our wait-free counter? So we need a way to detect that other operations in progress. We really can't do that with the CAS loop. I don't know if another thread, if I'm about to CAS current +1, I have no way of knowing another thread isn't about to do the same. Don't know. So we need a way to signal to other threads that we're about to do something. In particular, the thing that really matters most is we need to be able to tell other threads that we want the counter to be 0. Because the counter being 0 is really, that is the core of the difficulty of this problem. If the counter is 1 billion, and there's a few threads, incrementing, decrementing, nothing's going wrong. Like everything's fine up there, right? The counter is perfectly safe. No one's going to disagree on anything. The difficulty comes with threads agreeing whether the counter is 0 or not. You don't want one thread to reduce the counter to 0, another thread to increment it. Now it's 1 again, and the other thread goes, I didn't know it was 0. I didn't know. It wasn't my fault. The threads need to really agree for sure on whether the counter is 0. That's the core of this. If the counter is really big, nothing can go wrong. So is the counter 0 is the fundamental thing that the threads need to figure out how to communicate to each other, how to agree on. And so one big idea that we're going to use, right? We have an integer. We have plenty of bits. We're going to steal a couple of bits for this algorithm. This is the key idea number 1 for the wait-free counter. We're going to steal some bits. You've got 2 to the 64 possible values. You can deal with having 2 to the 62 possible values. That's enough. So we have our counter here. We're going to steal 2 bits to use as flags. Okay? So the big idea is these flags are going to be used for the threads to help synchronize on whether the counter is 0. And these are going to help the threads communicate with each other without an unbounded CAS loop. Right? These are going to be used to help the threads communicate and help each other rather than compete. So essentially, an operation wants to announce that the counter is 0, not by literally making the counter all 0 bits, but rather we're going to use the top flag to mean, I say the counter is 0 now. And any thread that reads the counter, if it sees the top bit set, is going to say, the counter is 0 now. Like, I believe you. Doesn't matter what those low bits actually are. We need this flag so that everyone can synchronously agree on the fact that the counter is 0. If that bit is set, it's 0. Otherwise, it's not. And the second flag we'll see in a moment, that's going to be used for some helping. That's so that threads can synchronize up and help each other if they splice into each other. We'll see that in a moment. So, step 1, let's try and now take this idea and make it work. So, we're going to start with a simpler problem. We're going to start with the wait-free counter without the read operation just yet. Because it turns out that adding the read operation adds a bunch of extra subtlety and makes the problem even harder. So we're going to start with a simplified version of the counter with no read. You just have your increment, if not 0, and decrement. Even without a read operation, those are still useful operations. You can use that to implement like a reader-writer lock, for example. So this is still a useful primitive if you delete read from the API. But it's also just a good stepping stone for this algorithm. So we're going to have our is0 flag sitting up the top in the high bits. And our decrement operation, does a fetch and sub, checks whether it's 1. So what do we do here? What are we going to do? Well, remember how fetch and sub works. this means the counter is 0, or at least we want it to be 0. The other threads might not agree that it's 0 yet. Someone else might want to increment it at the same time. Remember, we need to agree. The threads have to agree. So we see that the counter value is literally 0. It's all zeros. We now want to commit to saying the counter is 0 for everyone forever. We want to commit that in. We're going to do that by trying to compare exchange in the 0 flag, the high bit. Okay? So we're going to say a compare exchange. We expect the counter to be 0 because we just did a fetch sub 1 and got 1. So for at least for some brief moment in time, the bits in memory were all 0. But we haven't necessarily committed to the counter being 0 yet, but the bits were all 0. So we would like to commit to that and say to everyone else in the world, the counter is 0 by setting that flag. And now no one can ever disagree with us. Okay? So, but what can race with this operation? What else could be happening at the same time? Well, an increment could be happening at the same time. An increment may want to add 1 to the counter. What can it do? Well, we can't do an unbounded CAS loop anymore. So we have our tool. We have our fetch and add operation, which says I would like to atomically add 1 to the counter. Now you might start to see, here's how this magic flag comes in handy. Because what I can do is I can fetch and add 1 to my counter. If what I get back has that 0 flag in it, it has the top bit set, then I know I've just incremented the counter that had been set to 0, which means I'm going to pretend that I didn't increment the counter, because that top bit being set means forever and ever, the counter must now be treated as 0. Like, visualize it like this. I have my counter, it gets set with the 0 flag. If a fetch and add comes in and adds 1, who cares? Once that top bit is set, we never care about what is in the remaining 62 bits anymore. We never look at them. We just say, oh, that top bit is set, the counter is 0. Okay? And this is nice because it means a fetch add doesn't break this. Like a fetch add doesn't take the counter from being 0 to not 0. If the counter value was just literally all the 0 bits, a fetch and add now makes it not 0. That's the magic of hiding this flag in the topmost bit, is that a fetch and add now doesn't change anything. That flag was still set, it was set before, it's still set now. So the increment knows, oh, the counter was 0, and so it returns false. Right? It returns false because it sees that flag and says, the counter was 0, I'm not allowed to increment it. Okay? Question? I can't hear you whatsoever. Does it break decrement? Yeah, good question, right? It is not obvious that this algorithm is correct. Does it break decrement? We'll see in a moment. No, it doesn't, but we'll have to reason about it. It's not obvious that it doesn't. Yes, Fedor.
What happens if you do that while all the bits were 0? In that brief moment when the bits were 0 and the flag wasn't raised, you will get all zeros back and this false, so you say the flag is not set, but the count actually was 0.
Right, so what if the actual bits of the count, so Fedor's question, what if the actual bits were 0? That would pose a problem if a reader wanted to read the counter and saw 0, and then someone incremented it. That's why we will address that in a moment. That is coming up in a moment. But yes, those are legitimate, valid questions, right? There are some concerns here. Right, so our increments just, they happily go on, right? Incrementing the counter, they see the high bit. But what happens...
My question was, what does increment return? False.
What does increment return if it was all 0 bits and it successfully did a fetch add 1? It says it wasn't 0. We'll see why in a minute. Yeah, that's weird, right? We'll see why in a minute that's okay. It's weird. So what's going on here, okay? So, what if this compare exchange returns false? That is basically Fedor's question, right? If this compare exchange is false, that means we set the bits of the counter to 0. But then an increment came in and said, no, it's not 0, I'm incrementing. What do we actually do? Well, that means that what actually happened, like for real in memory, right? The bits were 0, then the bits were 1. And now the state of the world is that the counter is 1. But these operations were happening at the same time. These operations overlapped in their execution. So I'm just going to say that the increment happened first. I'm going to say the increment happened and actually took the counter from 1 to 2. Then the decrement happened and took it from 2 to 1. And you tell me, no, it happened in the other order. You're not allowed to just say what order it happened in. Well, I am. This is called linearizability. I'm going to say the decrement linearizes after the increment. I'm going to say that because these operations overlapped, you can't tell me one happened before the other. They were happening at the same time. I'm going to just say that the decrement must have happened after the increment. And you can't tell me, if all you have, you're not allowed to look at the bits of my memory while this is going on. I mean, Fedor saw the bits of memory were 0, but if you're not allowed to look into my memory, if all you're allowed to do is see the outcomes of these operations that were running concurrently, you can't prove otherwise that the decrement didn't just happen second. And what was output was a totally legal output. So some more terminology here we can drop. I've dropped a new term, linearizability, right? Essentially, a concurrent data structure is linearizable if you have any execution of their operations where they arbitrarily overlap, right? They are overlapping in arbitrary, nefarious ways. If their output is equal to some output you could have gotten from some sequential program, it's linearizable. Like there is an order that I could put the operations in, and if I ran them sequentially, I'd get that output. So my claim to you is, when this happens, when the CAS fails and the increment increments from the 0 bits, I'm going to just tell you the decrement actually happened after the increment. And I'm allowed to do that according to linearizability. That's legal. But it's kind of weird to wrap your head around, right? Because we know that truly in memory, right, the bits really were 0. But no one can observe that. Nothing in this at the moment can observe the bits being 0. So they can't prove that I'm lying. But now you might say, okay, I want the read operation back. I want to be able to read the counter. Well, now we're in trouble, because now you can read my counter and see that the bits are 0 and prove that I was lying about the order of the increment and decrement. You can be like, I read the counter and I saw 0, but actually then I read it a minute later, right? Counter was 1. We fetch sub 1, the counter is now 0. The read comes in, sees 0, goes to sleep. The increment comes in, resurrects the counter back to 1. The read returns 0. But now if the read reads again, it sees 1 and it says, I read 0, then 1. You lied to me. You can't go from 0 to 1. So that's why adding the read operation is very non-trivial here, right? If you don't need that read operation, right? As per the previous slide, if all you care about is the first two, this is a legal linearizable implementation of those two operations, because no one can observe the fact that the counter was ever 0. So that's a legal implementation of that simplified operation where I don't have a read. Yes, Fedor?
Something is missing here, which is there is some restriction on its use that prevents decrement from growing below 0. Can you state there is some kind of use pattern?
Yeah. So Fedor said there must be some way that I'm requiring that decrement never drops you below 0. Yes, effectively the API requirement is you're not allowed to call decrement unless you're certain you're not sending it under 0. This is true when you use it for reference counting, because you call decrement when you are the owner of a reference. So yes, the user of this API can only call decrement when they're certain it's not 0. That's not enforced by the library, that's enforced as a precondition. The user must know it's not going negative, and that's the case in like reference counting. Yeah, so that's something we don't enforce as the library. That's the programmer has to do that correctly. Yes, good point. Yes. What happens if we use what, sorry? If the user gets it wrong and decrements 0, well, I guess it's horribly bad. You like overflow negative, or it's unsigned, so you overflow around and all the bits are now 1, and everything seems pretty wrong at that point. It's just wrong. It's violating the precondition, I guess. It violates a contract. I think you have a talk about contracts. It violates that. Yes?
I think the way to think about this is just that for it to be legal for you to call decrement, you must have either paid counter or you must call the independent non-zero.
Yeah, so a good comment was, in order for you to call decrement, you should have been like the one who previously incremented it, which would be true for a shared pointer, or some other way you know that you own that count. Yes, Timo? It is confusing, I agree. This stuff is tricky.
You have to own the reference.
Right, so as a user of the API, right, you can only call decrement if you know for certain that it's not 0. That means your algorithm must satisfy that pattern. This would be true in reference counting if you have a shared pointer that owns a reference and you decrement it when you delete the shared pointer when it goes out of scope. You know that no one else is deleting your reference. That's yours. So this is enforced by the programmer using the API correctly. It is a precondition that you not call decrement unless you know the counter is definitely not 0. And you have that fact when you're doing reference counting. If your shared pointer is not buggy, at least, then you have that. So yeah, that must be enforced by the programmer. So, yes. Yeah, sorry, what was the comment? Right, so if it's a big number, it's like 1,000, you can decrement to 999. Yeah, you don't care about the precondition there, but you may care about it 999 decrements later or something. When the 999 real shared pointers go out of scope, and they're like, who took my reference? So that needs to be enforced by the programmer. The decrement is only called, the counter is definitely not 0. So the issue here, right, is the read, if we now want to add the read operation, we can't read 0 and return 0 because we can get this non-linearizable outcome, right? Like there's no world in which you can return 0 from a read and then read again and return 1. That means someone definitely resurrected the counter. So we need to prevent that. Okay, and this is where things get fun. So how do we prevent that? If the value is 0, we need some special handling. What do we do? Well, if the value is 0, we know something is about to happen. There's a thread that is about to do this. We've just detected another thread is about to do something very important. What should we do? We could wait for that thread to do that. I'm like, oh, I know someone else is about to do this, CAS. I'll wait for him. And we'd be blocking. We could just clobber him and change the counter in some weird way. That wouldn't be very nice. What do? We've just detected what another thread is doing. Let's help them. We know this other thread wants to compare exchange the 0 flag, and we've just come in and found that they're about to do that, but we got in first, because maybe we got rescheduled onto their core. So let's help them. Let's finish what they were about to do for them. That is the key of wait-free design, is helping, right? We've detected an operation in progress, and rather than clobbering it or just waiting and blocking for it to finish, we are going to help it finish. We're going to do its operation for it. So did we fix the bug? Do you have a comment on that? Good point, yes. Did we fix the bug? Yes, but we added another one. So the issue is if a read helps the decrement, then it means that the counter is 0, but none of the decrements return true. And you're like, well, who set it to 0? Like, No one's claiming responsibility. And this matters very much in reference counting because the guy who set it to 0 is the guy who has to delete the stuff. So if no one takes responsibility, nothing gets deleted, this is bad. So we're not quite done yet. We need one more little ingredient. We need a way for the decrement to then take credit for the helping. Well, I said we're going to steal 2 flags, 2 bits from our 64 bits. Let's use the other one. So my top bit is the 0 flag, and I'm now going to use a second bit that says, hey, you got helped. I'm going to put in a bit that says, I helped you set the counter to 0, by the way, just so you know. So now, when the read helps, it sets this help flag. When a decrement comes in, it tries to compare exchange. It wants to set the 0 flag. It fails. Well, it could have failed for 2 reasons. It could have been an increment, in which case we invoke the magic word, linearizability, and I say the decrement happened afterwards. Everyone is happy. The world is fine. If it failed because a read helped it, then it should try to take responsibility. It should try to say, it was me who set the counter to 0, because someone needs to take responsibility. So what we try to do is we detect, is the help flag in the bits? If it is, at this point, I know that the counter is 0. I can clobber any other bits of that counter. It doesn't matter. The low bits at this point are totally irrelevant. I'm just going to now exchange away the help flag. I'm going to replace the bit pattern with just the 0 flag, which is 1 and then all zeros. I'm going to try to exchange out the help flag. And I need to see whether or not I'm the one who got it. Keep in mind, there could be multiple threads doing this at the same time. You could have had a bunch of increments and decrements going 0, 1, 0, 1, 0, 1, 0, 1. There could be 10 threads who all think they're the one who set the counter to 0. They can't all take responsibility for it. Exactly one, and only one, must take credit for the decrement. We do that by exchanging out that help flag. Whoever gets it gets credit. Right? Because remember, exchange replaces the value and tells you what was there. If what was there had the help flag, you're the one who took the help flag. You take credit. It was your decrement. You are the one who set the counter to 0. Otherwise, someone else got it. And this is our final correct algorithm. I claim that we finally got rid of all the very subtle bugs, but it was hard, right? This stuff is not straightforward. There's a lot of subtlety to think about in designing weight-free algorithms, but that is really the bread and butter of it, is this helping scheme, right? We saw another operation in progress. Instead of clobbering it or just waiting, we helped it. We helped it succeed, and then we also helped it return the right answer, because it had to return true when it decremented. So I promised you some benchmarks, okay? So this is a weight-free algorithm. Is it good, though? I promised you some benchmarks. Since this is mostly a talk about weight-free in theory, only a few benchmarks, not a lot. But like I said, you should always benchmark to confirm, okay, this is a weight-free algorithm. It's probably better than the lock-free algorithm. But you should benchmark to be sure. So here's my experiment. So I implemented an atomic shared pointer. This is basically the one I talked about last year at CppCon. And in it, I put in this counter. I tried 2 versions, the weight-free counter and the lock-free counter, and I compare the performance. So what we care about is the latency of the load function, because the load is the guy who calls increment if not 0. So it's the store operation doesn't actually call that, so it doesn't need to do this. So we benchmark the load latency, and we compare lock-free and weight-free. And in this experiment, at least, when I just have p threads all basically spamming load on the atomic shared pointer, what we see is more or less better latency across the board for the weight-free counter. That's pretty good. But are we done? Is this enough benchmarking, or should we do some more? Should probably never just benchmark, one workload, one setup, and then draw your conclusions, ship it. No, you should probably benchmark a few different scenarios, a few different workloads. So we could try, okay, benchmark 2. I'm going to have half my threads loading and half my threads storing to my atomic shared pointer using these weight-free and lock-free counters. In this case, we can see that the weight-free counter is still ahead, but by less. The gap has closed a little bit. It's only slightly ahead now. And in fact, you can see there's even, some cases, it's not always ahead, but it's ahead most of the time. It's not strictly always ahead in every single one. Okay, so there is a difference, right? Like depending on the workload, we do get a different performance profile. And now we can go even more extreme. How about if we're only doing 10% loads and 90% writes, so 90% stores to the atomic shared pointer? Well, now you can see that at higher thread counts, so at lower thread counts, the weight-free one's still marginally ahead, but at higher thread counts, this is, by the way, I should have mentioned, this is a 28-core machine. I'm not just randomly picking 2856. This is saturating the cores and saturating the hyperthreads. It's a 28-core single-socket machine. So you can see that at enough threads, eventually, with the correct workload, the lock-free one does pull ahead. So this is why you should benchmark. Because whether or not the weight-free algorithm was better depends on your workload. It depends on how often are you loading and storing from your atomic shared pointer. You can't just do one benchmark and draw your conclusions, right? So what algorithm is best depends on the workload. How many reads versus how many writes? How many threads or cores? Weight-free in this case was better in the read mostly workload because that's when you have the most contention on incrementing the counter, because when you do lots and lots of loads, that's lots and lots of increments on the counter. As that dies off and we do fewer and fewer loads and we have more and more stores, there's less contention on that increment operation and the lock-free algorithm pulls ahead. Because it turns out that if you just do a compare exchange and it succeeds, that's usually faster than the weight-free algorithm. If that loop doesn't loop, it's actually really good. And that's what happens as you do more stores. So the take-home messages here, progress guarantees, right? We classify our algorithms not just by Control-F, look for the word mutex. We look at their progress guarantees, right? Lock-free algorithms, they guarantee you that at least one thread makes progress, but a weight-free algorithm says, I can do better. Every thread makes progress. And in weight-free algorithm design, the key trick was helping, right? We encounter another operation in progress, and instead of clobbering it or blocking, we help it complete, right? We saw that another thread was trying to set the counter to 0, we helped it. Instead of clobbering it, we helped it along. And that way, it didn't get stuck or give the wrong answer. And performance implications, don't just guess about performance, by which I mean don't just guess and ship it, but do hypothesize about performance, right? By analyzing your algorithm, do some theoretical analysis, hypothesize about what might be faster, and then test it, then benchmark it. And that is weight-free algorithm design. I hope you learned something useful today. Thank you. If you have questions, come up to one of the microphones. Yes, Timo.
So thank you for the talk. I did indeed learn something new, so that's awesome.
Good,
Thank you very
it worked.
much. I also observed that these techniques have something in common with like more traditional lock-free programming, in the sense that you think you're done, and then you're like, oh, but then there's this other weird edge case that we have to worry about. My algorithm's broken. Then you fix it. Are we done now? Oh, there's this other even more weird edge case that we forgot to account for. So my question is, how do you know when you're actually done when designing these algorithms? Because that's something that I've always been struggling with. How do you know that you're done now?
Right. How do you know that you're done? That's
haven't
tricky.
Overlooked another weird use case where there's one more thread doing something weird that you haven't thought of.
That's tricky. I mean, we essentially want like a proof of correctness, right? So many people work on formalizing algorithms and doing formal proofs of correctness, like actually putting your algorithm into a proof system, a theorem solver, and trying to essentially prove assertions about your algorithm and have it logically tell you that, yes, this is definitely true. Some people do that. I don't personally do that, but there are lots of people who work on that sort of thing, formal verification. Another option is to essentially write, a proof on paper, the kind of proof you'd see in like an algorithm theory paper, not a formal, computerified proof, but a proof using writing and words. Usually you do that by proving the linearizability of the algorithm. And that typically comes down to identifying where the linearization points are. When I was talking about the decrement operation, right, I said it linearizes, like we linearize the decrement after. And the idea is that the decrement doesn't linearize until it fails that CAS, until it fails the compare exchange. It does not linearize when it does the fetch and sub, because it's still something else could come and change its outcome. It linearizes at the point that it does the compare exchange, essentially. And you can try and reason about this write down a mathematical proof that, okay, I claim these are the linearization points, and I claim that now if you give me any concurrent overlapping execution of these algorithms, they'll behave as if they went in order by their linearization points. So this is the kind of thing that that people do, and if they try and write a formal proof of correctness for these sorts of things, but it's hard, right? Like it's proofs. It's like proofs class you take in CS undergrad and grad school. Like, it's hard to prove stuff is correct, and there's no one-size-fits-all technique that just does it, right? Every algorithm is different, but you can also stress test it and see if it's segfaults. That'll tell you there is a bug, but it won't necessarily prove the absence of bugs. But it's a good start. It's probably what most people do as well. Yes.
Yeah, I was actually going to say my approach has always been just run it with 1,000 threads for a day and see if it gets itself into an invalid state somehow.
Yeah, that'll do it unless, of course, your test doesn't do the corner case scenario.
Right.
So that may or may not catch it.
Yeah. Could we back up to the final version of the algorithm out of curiosity?
Yes.
Oh, actually, and I just see that I misread originally, so I'm good. Thank you.
Perfect. The algorithm is still correct as far as we know. It's not broken yet. Other mic, yes.
Hi, Daniel. Thanks for the talk. Quick question. So on ARM, compare exchange strong is a loop. Does it still qualify as weight-free?
On ARM, compare exchange strong is a loop. Is it weight-free? I guess the theoretical answer is weight freedom is defined with respect to a magical abstract machine. There's no such thing as ARM. So does it qualify as weight-free? That's up to ARM users to decide. But in the theoretical sense, right, we don't talk about actual hardware, right? We talk about some model of computation. And we assume in our model of computation that compare exchange, it works if no one else is going to contend with you. I guess that's up to ARM users to decide for them, because I guess the theory community doesn't care about real computers. Is the not very satisfying answer. Yes, Fedor.
Want some clarification on like the very first slide, because I feel like you kind of changed the rules on us when you described lock-free blocking versus lock-free. So
the very first slide, all right.
Okay.
No, not that early.
Well, the one where you define blocking, non-blocking.
I see. Here we go.
So when you say blocking, like it's possible that no progress is being made, and the argument you made was the thread that is holding the lock can be suspended.
Right.
Now, if we're willing to consider that event, then basically there is no such thing as weight-free, because again, a thread can be suspended, therefore it's not making any progress, then not every operation is making progress. So it seems like choose your rules one way or the other, but be consistent.
Yeah, our definition definitely needs some, qualifiers, like what exactly does progress mean? And we need to maybe be a bit more precise in some of these terms, right? Like, I guess when we say progress, we mean if you're actually scheduled on and doing something. So if you're scheduled off, well, of course, you can't make progress, and so we wouldn't expect you to make progress.
But in that case, a blocking algorithm would actually only block if you encounter a true deadlock.
Yeah, so I guess blocking, so maybe my blocking should have said something stronger. Yeah, I guess I didn't think too hard about defining the non-interesting bottom two ones on the slide. So yeah, perhaps we should have said blocking can deadlock, right? Like not just no guarantee, but we should have been even scarier and said, it'll actually deadlock. Yeah. Good point. I agree. Yes.
Thank you for the talk.
Thank you.
The question is, when you compile it to run on a system, do you need to check is lock-free or always lock-free? Because on 64-bit, it will be not always lock-free.
Right. So if we're doing this again on a real computer, right? We do, of course. Our theory is baking in the assumption that our atomic operations are constant time lock-free. So we do need to test if we put it on a real computer that it matches our theoretical assumptions, yes. And I'm being told to get off the stage because the next session is coming. So thank you, everyone. I'll happily take more questions outside.